L is lambda, and we look at this, we've got 2/3 of lambda here equal to L, which means that lambda equals, I'm sorry, not 2/3. We've got 3/2. Putting the answer down there, we have 3/2 of the lambda. We have 1.5 waves equals L, which means lambda is equal to 2/3 L. All right, see how I did that? I said here I've got 1.5 waves. Here's one wave and another half a wave. So 1.5 waves lengths equals L, which means lambda equals 2/3. So now let's take a look at our wave equation. Our wave equation says that velocity equals frequency times wavelength. And if we want to know what these frequencies are, we solve this. We get frequency equals velocity over wavelength. Not v, velocity over wavelength. That's terrible. Velocity over wavelength. And so if I look at this first one, I get that frequency is equal to, we'll call this the first one, F1. Frequency is equal to v, whatever the speed of the wave is on the string, over 2L. And if I look at this one, it's the second one. Frequency equals velocity over wavelength, which is just L. And just, you'll understand why in a second, I'm going to go ahead and just say this is 2v over 2L. See, so I get that 2L and that 2L, because a pattern is going to emerge. And then if I look at this one, F3, it's V over 2/3 L, right? V over 2/3 L. So I have a 2L there, but then the divided by 3 I can bring up in the numerator, and I have 3V over 2L. So if you look at this, I have 1V over 2L, 2V over 2L, 3V over 3L, and in fact, if you go ahead and do the next one for this length of string is going to look like this. Sorry, that's horribly drawn, but you add one more node and antinode, right? You add one more node and antinode out there. So, node, 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 5 nodes, 4 antinodes. Okay? And what do you have here? Here's one wavelength and 2 wavelengths. So lambda, so 2 times the wavelength is equal to L. That gives us lambda equals L over 2. And if you do this, this is F4. This is V over L over 2, so it's 2V over L, which is just 4V over 2L. Multiply the top and bottom by 2. So V over 2L, 2V over 2L, 3V over 2L, 4V over 2L. The next one would be 5V over 2L. And this allows us to just make note of a pattern. So what we can say is for the inharmonic, which would be the first, the second, the third, the fourth, the fifth, so on and so forth, it's going to be equal to N times V over 2L. 2 times the length of the string, where N is equal to 1, 2, 3, so on and so forth. Okay? And so that's going to be an equation for all of the harmonics, the frequencies of the harmonics that would be on a standing wave, that would create a standing wave on a string. Other frequencies would get all jumbled and mess up, and it wouldn't look very well. Okay? N equals 1 is the first or fundamental harmonic, that's this one, and then so on and so forth. Okay? Now, let's look at something that isn't standing wave on a string, but how about a standing wave in a closed pipe? Okay, so a closed pipe. And we're going to go through this one a whole lot faster. So let's say we have a closed pipe. Both the ends are closed, like this, and if the ends are closed, it means the air molecules can't vibrate there. Just like up above here, the strings couldn't move at the ends, so they were both nodes. That means we have to have a node and a node. Now, if there's just nodes there, it's nothing, it's not interesting. So the first standing wave is, as we add sound into our tiny little hole here, the first standing wave we gave would be a node, an antinode, and a node. Well, that's just like this one, node, antinode, node. But in this case, sorry, the nodes, uh, the nodes and antinodes, they correspond to high and low pressures. So we end up with, and we can draw, we're not really going to draw in the high and low pressures, but we can draw in the wave very similarly. All right, this is going to be where the compressions, and these are going to be the low ones. Okay, so that's the first one, and this gives us the exact same result that we had up here, right? Lambda is equal to 2L, and so the first harmonic is going to be V over 2L. Well, if we do the next one, the next harmonic that fits, again, we have to have node, node, and then we're going to do the same thing. We're going to add in an antinode, one node, and an antinode. And so you end up with this, right? This isn't about crests and troughs, it's about pressures here again, but the only way we can really draw them is to draw them like they're transverse waves. And look at that. It's the same result as here, which means we're going to get this same result. And if we do the third one, you add another two nodes now, you add another node, so you're going to get something like this. For some reason my drawing is getting worse, but node, 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 antinode, antinode, antinodes, right? The antinodes, antinodes, antinodes are that area. And again, that matches this one, and the fourth one will match this one. So it turns out that for a closed pipe, this same equation works. In fact, this equation works as long as you have a standing wave where the start and the end have to be the same, either both nodes, or we can do another case here where they're both antinodes. So let's say we had a pipe that was open at both ends. So this could be some sort of wind instrument, and it's open at both ends. All right, let's make this a little straighter and a little wider. So let's look at this one. We have a pipe that's open at both ends. That means at this end we can have an antinode, and this end we can have an antinode, and then in the between, in order to get away, we have to have a node. So what do we get? We get something that looks like this. If you look at it, up here before, this was half a wave. You go along, and then there'd be another half a wave out here, just like with the string. Well, look at this. This is still half a wave. You start up here, you go down, and to complete the wave, you would go back up. So this is half a wave, which means our wavelength is just the same as it was here, 2L, which means the frequency is going to be V over 2L, where it's the speed of sound in the speed of the sound in that pipe, and then 2L is the wavelength. Okay? What happens with the next open pipe? The next open pipe, we add another node and antinode, so we're going to have two nodes in the middle now. So we have an antinode, and we'll have an antinode in the middle, node. Node is going to do like this. Something like that. Okay? And if you look at this one above, this was one full wavelength. This is also one full wavelength. Down and back up. Okay? It's one full wavelength, which means, again, we have that same wavelength of lambda equals L. Here, lambda equal 2L. And then over here, we're going to get this same one, this 2/3. We're going to get again. So if we draw this in, we have to have three nodes in the middle, and it gets harder and harder to draw, but up, down, and up, and up, and down, and up. But we're always adding one more node and one more antinode. So antinode, antinode, went two antinodes, one node, to three antinodes, two nodes, to four antinodes, and three nodes. 1, 2, 3, antinode, 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 right? 4 of those antinodes, okay? And so we're going to end up with this same thing that you do it again. This is one wavelength here and a half a wavelength. So it's the 1.5 wavelengths equals L. We get the same thing. This is 2/3 L, 2/3 L, sorry. And so it's going to give us the same frequency for that one. So this is again following this same pattern for frequencies of harmonics. This works whenever it either starts and ends with a node, or starts and ends with an antinode. So as long as it's symmetric, right, where the start is the same as the end, this equation is going to work. Now, is there a situation where this equation doesn't work? And the answer is yes. What if we have a pipe that is closed at one end but open at the other? That means at this end we're going to get a node, and at this end we're going to get an antinode. And then there doesn't have to be anything in between. We can't go antinode antinode node, and it can't go antinode node node. So antinode node, that's what we have to go to. And so it's going to be this. Something like that. And if you look at this, this is only a quarter of a wave. It has to come down, there's half a wave, and then it has to go back up. There's the full wave. So this is only a quarter of a wave. So that tells us that 1/4 of lambda equals L, which means lambda is 4 times L, the length of our pipe here. Okay? The next one, let me get rid of this little line here. The next one that we'd get, we add on one more node, one more antinode. So we add on a node. We still have to have a node here and an antinode here. It's still antinode, node. We have to have an antinode. Then a node always has to go that alternating pattern, right? So it's going to go something like this. Okay? And if you look at this, we don't have quite a full wave. A full wave would be out here, right? That'd be a full wave. So what do we have? We have 1, 2, 3/4 of a wave. So 3/4 of lambda equals L. And so lambda is 4/3 L. And then let's do the next one. The next one, just so we can make sure we get the pattern, and we could keep going. We have to add one more node and antinode. There we go. So now instead of 2 nodes, we have 3 nodes. Node, node, node. And it'll be antinodes in between. Antinode here. It's going to come down, up, down, sorry. And then down, up, down like this. And if you look at this, we have one full wave here going up, back down. There's one wave, 1 1/4 waves. That's what we have right there. 1 1/4, that's 5/4 lambda is L, right? That's 1 1/4, because we have 1 1/4 waves in the length of L. And then that means that lambda is 4/5 L. Okay, so let's write the frequencies for these. This is our first one. It's, remember, F is V over lambda. So it's V over 4L, because that's what lambda is, 4L. This one, I'm not going to put a number there yet. This one is V over 4/3 L, which is 3V over 4L. So we have that 4L again, but this time we went from 1, not to 2, but to 3. 1, 3. Let's see what happens with this one. F equals V over 4/5 L, which is 5V over 4L. So we have that 4L. But now look at this. It's 1V over 4L, 3V over 4L, 5V over 4L. So the denominator is different. Up here we had 2L in the denominator. And we had that in V, we had 1V, 2V, 3V, 4V, 5V over 2L. But now we're going 1, 3, 5 over 4L. So this pattern is following Fn equals NV over 4L this time. And N isn't 1, 2, 3, 4, 5. It's 1, 3, 5, 7. It's all the odds. So with this one, we don't have any of the even harmonics. We only have the odd harmonics. Okay? 1, 3, 5. So this isn't the second harmonic, it's really the third harmonic. There's no even harmonics. And this is the fifth harmonic. The even harmonics, they just don't show up on this. And this is when we have this anti-symmetric. This is when you have this is when it starts with an antinode and ends with a node, or starts with a node and ends with an antinode, one of those two things, where it's not starting and ending with the same thing. It gives you this equation. Now, you don't have to be able to derive these equations, but you do have to know when to use each one and what they look like, or which situations they belong to. This is the one for where the start and the end aren't the same. This equation is for where they are the same. It starts with a node, ends with a node, or starts with an antinode, ends with an antinode for strings or pipes. Okay? Now I'll throw a little extra on here. I just want to talk to you about a couple things just for the music fans out there, and it's timbre, if you know that word. So if you've ever wondered why is it if I play a note on a piano and I play the same note on a violin, or I play the same note on a flute, or someone sings the same note, why do they all sound different? And the answer is because of this. This is what's known as the richness of the sound. And if you were to take each of those things, like a guitar string or vocal cords and anything like that, basically what happens is there will be a fundamental frequency. And this fundamental frequency, when n equals 1, that is equal to what the note is you're playing. It's the pitch of the note. So the first frequency is the pitch of the note. And so if we went through and we took each of all of these frequencies that would make standing waves on the string. So imagine it's a guitar string. You pluck the guitar string, or you bow the violin string, and what's going to happen is you're going to get all of these harmonics. Those are going to end up staying on the string because they fit on it real nicely, and they don't become a jumbled mess and cancel themselves out. They resonate. This is a type of resonance. And what you end up with is then these are the things making up the sound. And different strings will have different amounts of these different harmonics. This first harmonic, this fundamental one, that decides what note you're playing. Okay? And then how a guitar sounds different from a violin, sounds different from a viola, sounds different from a cello, all playing the same note, is they have varying amounts of each of these harmonics. And same thing with something that was a pipe. The pianos, their strings, pipe instruments like flutes, trumpets, and stuff like that. It's the same sort of thing, but with the pipe resonance. And what happens is you could actually go through and say, maybe this is, I don't know what it is, I'm just kind of making this up, but maybe you have a whole lot of the first harmonic, it's very strong, so this is like the amount of it you have, the amplitude of it. And so the first harmonic's really, kind of strong on one instrument. The second harmonic's really weak. Maybe the third harmonic's not there at all. Maybe the fourth harmonic, there's a lot of it. And then, maybe this one there's a lot of too. And this is the second harmonic, and the third harmonic, and the fourth, and the fifth harmonic, and so on and so forth. And then another instrument playing the exact same note, say, maybe they don't have as much of the first harmonics not present, and maybe none of the second harmonic, and a lot of the third harmonic, and a medium amount of the fourth harmonic, and a whole bunch of the fifth harmonic. So it's the same note, but the underlying harmonics, the amount that those harmonics are there, how loud those harmonics are, the amplitude of those harmonics will vary, right? And it varies, and it makes these two notes both playing the same frequency sound with the same fundamental harmonic, making that same note. This determines the note. This determines all these other stuff. The amounts of these harmonics determines then the richness of it, and whether or not it sounds like a violin, or sounds like a guitar, or sounds like a piano, or sounds like a trumpet. Okay? And that's called timbre. And the different amounts of those harmonics determine that. Now the last thing I'll talk about is stringed instruments. You ever heard of someone, you play the harmonics. So what you could do is say, for example, I was playing a guitar, and you lightly touch your finger on the string in one position. So let's say I had this string, and I plucked it, and I got this harmonic to appear on there, and this harmonic appears on there, the first one, the second one, the third harmonic appears like this. I know it's getting kind of messy, but the third harmonic is like that. And let's say I just lightly touch my finger right in the middle. Well, the first harmonic wants to vibrate. It has an antinode right there, which means by touching that right there, you know, the first harmonic, I have the second harmonic, and I have the third harmonic, but I lightly touch the middle, it totally cancels out that first harmonic. It doesn't allow it to vibrate. So I get rid of the second harmonic, or the first harmonic. But look at the second harmonic. The second harmonic looks like that, right? And the second harmonic has no amplitude in the middle. So if I put my finger there on the string, the second harmonic note doesn't notice. It's not affected at all, right? So the second harmonic stays. Now look at the third harmonic. The third harmonic has an amplitude in the middle, right? So the third harmonic gets canceled out. What about the fourth harmonic? My picture is getting a little messy. So let's say this is my string again. The fourth harmonic looks like this, right? And this is the middle again. Well, I touch my finger there. The fourth harmonic has no amplitude there. So the fourth one, it doesn't notice either. Doesn't notice. Okay? And so what happens is if I put my finger right in the middle like that, I end up canceling out some of the harmonics. I don't let them exist, but other ones I leave behind. The ones that have nodes at the location where I put my finger, they don't notice that I've put my finger there. The ones that have antinodes or amplitudes that are not nodes, they are not nodes where I put my finger, they don't get canceled out. And so doing something like this, if you've ever done it, you just touch your finger lightly on the string. You can do this on the violins, guitars, and stuff like that. It's called playing these harmonics. And basically you're forcing any of the harmonics that would be present on that string that would not be nodes at that point where you're touching the string to cancel out. And the only thing that gets left behind are the ones that had nodes at those locations, and it gives you a different sound when you do that, when you play it. And you do it at different locations on the strings, and you're playing different harmonics. All right? So that's a little part, just a little bit of extra, and I think that's pretty much it for standing waves.